let's suppose f of x, y approaches L1 as xy approaches a point AB. And then a long path C1. Well, that's going to be something new. You'll see how it works. And also the same function, f of x, y, approaches L2, which is actually not the same as L1. All right? As x, y approaches the same point, but in this case along a different path, then the limit does not exist. So this is the two-dimensional or the multivariable analogous to the idea of the two limits not coincide from either side, but in this case we don't talk about it from the sides, you know. So the idea here, okay, again, we're going to show that a limit does not exist by considering different paths. Right now there's a tricky part right here. You'll see. So number one, well, every time you have a limit problem, direct substitution, that is 0 squared minus 0 squared over 0 squared plus 0 squared. Everything squared, that means 0 over 0. Well, this is good because that means we could potentially do some algebra to divide out any of those factors that it's causing the 0 over 0 indeterminate form. But if you observe this expression closely, well, the numerator is a difference of squares. I think that's clear. But the denominator, x squared plus y squared, that's a sum of squares, which is prime. I mean, you can still factor it out. You know? However, you would need to go through the field of complex numbers in this case. And well, this is real variable calculus, not a class for complex analysis class. So, well, that'll be something else. Well, so what are we going to do? Well, in this case, they're not asking us to compute the limit. In fact, they're telling us that the limit does not exist. They're asking us to show that. How are we going to show that? Well, so they're asking us to consider two different paths. Well, actually, I'm going to do three, not two. It doesn't say how many. I'm going to do three. So, for instance, what if I go about x equals to 0? Okay. So the first path, along x equals to 0. So here is what we're going to do. So we're going to compute the limit, and I'm going to replace x equals to 0 for every instance of x you see in the limit expression. That is 0 squared minus y squared over 0 squared plus y squared, everything squared. Now, notice how our limit expression only depends on y. So this is no longer a two-variable limit. This is just a single variable limit. So we don't need to put x approaches 0 and y approaches 0. We only need to put the y approaches 0. So the notation here is very important, right? Okay, so that's going to leave us with limit negative y squared over y squared as y approaches 0. And well, negative y squared over y squared, that equals to, okay, the limit y approaches 0, that's a negative 1 squared, which equals to 1. All right? So that equals to 1. All right. So that's the result of the limit. That is, if we go about x equals to 0. But I mean, what does that mean to go about x equals to 0? Again, so we want to approach the origin, 0, 0. So we're going to draw a disk around the origin. And in this case, well, we are approaching about path x equals to 0. That means either from the top along x equals to 0 or from the bottom along x equals to 0. So that's the vertical line, x equals to 0. Okay, let's try a different path this time and see what happens. So number 2, the path y equals to 0. Okay? So this is what we're going to do this time in a similar way we did it with the previous path. So I'm going to have limit, so x squared minus y, which is 0 squared, over x squared minus another 0 squared. Everything squared. But in this case, notice how we get a limit expression that depends only on x, no more y's right here. So that'll be as x rather, approaches 0. So that's going to leave us with limit x squared over x squared, quantity squared, x approaches 0. All right. So what is this? Limit another 1 squared as x approaches 0, and that equals to 1. Okay, so at this point, you might argue, well, so for this path, we're getting the same results, right? I mean, if we think of the one-dimensional limit, or the functions for one variable, rather, the limit from the left, the limit from the right, well, they're the same. So in this case, for different paths, we're getting the same. So, but here's the thing, guys. Well, so if you consider again this disk, how many ways to approach this center point can you think of? I mean, how many points does that circle have? Infinitely many. So, do you have time to try all of them? I don't think so. So what I'm trying to say is that 2, 3, or 4, 5, 17 paths, it's not enough. It's not enough to prove that the limit exists. In fact, they're telling us that the limit does not exist. So in this case, what we're trying to find is that path that is going to change the limit values, and therefore it's going to be on a does not exist limit. So I'm going to try a different path. Okay, so number 3, half y equals to 2x. Okay, that means I'm going to go along the diagonal line y equals to 2x, which contains the origin, by the way, right? So actually, you need to be careful about the path you choose. You cannot just put, ln of x or e to the 5x, because those functions you choose to as your path may not contain the center point we are approaching to. All right, so what are we going to do here? In a similar way we did for the first couple of paths, so limit, I will replace every instance of y with the 2x here. That means x squared minus y, which is 2x over x squared plus 2x. All right, so let me highlight it so you can see it. All right. So, okay, and again, this limit is going to be one with one single variable, that is just x. You don't need to put y approaches 0 anymore. So that is simply x approaches 0. Just get rid of the y in the notation. All right, so let's simplify this. So limit as x approaches 0 of x squared minus, careful, 2 squared x squared, that's minus 4x squared, divided by x squared plus 4x squared, quantity squared. Okay, so x squared minus 4 squared, that's equal to limit, that is 3, or rather negative 3x squared over 5x squared. Everything squared as x approaches 0. Now, the x squareds are going to get canceled, of course. And that's going to leave us with limit x approaches 0 of negative 3 over 5, which is 9 over 25. So this is the argument you're looking for to show that the limit does not exist. Yes, you got 1 and 1 for the first 2 tries. Yeah, that's right. However, the third one, another path in this case, gave us a different limit, and this is how you show that the limit does not exist. All right? So this means, okay, let's make more sense out of this. This means that if we approach along x equals to 0, that is vertically if we will, our limit is 1. If we approach horizontally, y equals to 0, that also equals to 1. However, if we approach as a diagonal line, the z value obtained is 9 over 25, which is no longer the same result as in the previous 2 tries. All right? Okay, so in some cases, so we need to try. We need to check different trajectories, different trials here. But in some cases, they will give us the path, and be careful how the paths are given. In some cases, they may give us a function of x. In some other cases, they may give us a function of y. So let's have a look at the next example to illustrate that idea. So we're asked to compute, or rather to show that another limit does not exist. All right? It does not exist. So that is, okay, number one, along y equals to x, that's path number one, that is limit, I will replace every instance of y with an x. So that is x times y, which is x, and x squared plus x to the fourth. And I'm going to highlight the x we are replacing this with. This is x because of this path. All right? So as x approaches 0, and that's just as x approaches 0 because we no longer have the y's. Okay? So that's just a single variable limit. So that's going to take us to the following. Limit x cubed over x squared plus x to the fourth power as x approaches 0. Well, so in this case, if we do the direct substitution, that's for sure going to give us a 0 over 0. All right? So, but well, that means we could potentially do some algebra to simplify the expression. Yes.
Does the negative in the sign of the expression?
Oh yes. Let me take it out of the limit. Thank you. Thank you. So yeah, that matters. So, or actually, let me just leave it inside. It might be better. Yep. Okay. So it looks like I could factor out an x squared in the denominator. So that is limit as x approaches 0, that's x squared in the denominator times 1 plus another x squared, x cubed, and then we can divide out two powers. Divide out two powers, that's going to leave us with 1 power, and that's limit of negative x over 1 plus x squared as x approaches 0. And we're good to go and evaluate this limit because that's going to leave us with, number one, negative 0 over 1 plus 0 squared, and that's simply 0. So that's the limit going in the direction of y equals to x. All right. Let's have a look at the second version. Okay, so that is number 2. X equals to y squared. All right. So that'll be then limit. So we will replace the x's with y squared times another y squared by default, and then x squared, which is going to be replaced with y squared. Don't forget to square this guy, plus y squared. As y in this case approaches 0, that'll be negative y. Oh, limit first. Which one?
The second one.
Oh yeah, the second one, right? Yeah, y to the fourth, and that's negative y to the fourth over y to the fourth plus y to the fourth. That is as y approaches 0. And what else? So combining like terms, that's a limit negative y to the fourth over 2y to the fourth. As y approaches 0, see how we divide this out? That's the limit of negative 1/2 as y approaches 0, which is negative 1/2. And with this is how we show that the limit does not exist by, well, in this case, we're given the different paths and we're getting two different limits. All right, question for the reflection or to like expand the idea. Well, let's explain why the path y equals to cosine x. It's not an appropriate path, but sine y equals sine of x, it is. So why is this?
Sine goes to 0.
Which one?
Sine goes to
Sine goes to 0. Okay. And okay, you're in the right track. Okay. Yes.
Like sine passes through the origin while cosine doesn't.
Exactly right. While cosine, whose graph looks like this, and sine looks like this, sine contains the origin, but cosine does not contain the origin. That's why it's not, right? So again, that's why that's what I was discussing in the previous example. So you can go through the origin using pretty much infinitely many paths, but not just any of the infinitely many paths available. Can you go through y equals to e to the x? Not in this case, because e to the x does not contain the origin. What about e to the x minus 1? There you go. You could use e to the x minus 1. I mean, you would have to square binomials. It might be an ugly looking limit, but well, it could work to show that the limit does not exist. All right. So to wrap up this section, let's have a look at continuity. Well, that's another very important property of functions. Well, you learned that in calculus 1 for a function of a single variable. What are we going to do? Just add 2, 3, 4, 17, 97 variables, as many as you want, and determine its continuity. Well, maybe not that many variables, but I mean, I want to say is there is no limit as to how many variables you can add to a function. So, the idea of continuity, well, number one. So, if you have, for instance, a function, well, let me just recall the single variable case, So, you want to determine whether a function f of x is continuous at x equals to a. All right? So, number one, you want to make sure two things. Number one, the function is defined, all right? I mean, because continuity, it's about drawing, in essence, it's to draw the graph of a function without having to lift the pencil or the pen, whatever you're using. That means if you have a hole or a gap or an asymptote, well, the function is not continuous because you would have to lift your pencil to keep drawing the rest of the graph. So, number one, granted is that the function is defined. That is, condition number one, f of a is defined. Number two, the limit exists. That is, the limit from the left, the limit from the side agree. That is, limit f of x as x approaches a exists. All right, and number three, condition number three, and most important, that is f of a equals the limit of f of x as x approaches a. So that's essentially combining conditions 1 and 2. So there were three conditions we needed to check for a limit to exist. All right, but what are we're going to do? So just add one more variable or two or three, I don't know, and the idea is going to be the same. So you need to make sure that for a function of two variables, the limit is equal to the value of the function. All right. So, well, and in general, continuity, it's about finding the domain again. So because again, a function, it's continuous in its domain. So all you do is simply rephrase it, if you will, and say, well, the function is continuous at this interval, as opposed to the domain of the function is this. It's the same. So the same guidelines to find domain are going to come back. All right? Let's have a look at and discuss the continuity of each function right here. F of xy equals the cosine of xy divided by x squared plus 1. Okay. So this is a multi-layered function, a composite function. That is, there is a cosine and then there is a rational in the angle for this function. So, well, the cosine function is, what's that? It's continuous for all real numbers, all right? Now we need to have a look at the inside, at the angle. And notice we have variables in the denominator, that x squared plus 1. However, is x squared plus 1 ever 0? Never, right? So yes, if you try to solve the quadratic equation, that's going to give you, in this case, imaginary numbers, not real numbers. So that means it's continuous for all ordered pairs x, y that are in R2. That is, rather than for all x in the real, for all y in the reals, we can combine it into one single expression, and for all ordered pairs that are in R2. If you want to use the domain notation, all x, y's that are such that x is in the reals and y is in the reals as well. Alright? So that is where the function is continuous at its domain, essentially. I mean, for letter B, what about it? So f of x y equals e to the y over x. Well, number one, again, we have another multi-layer function, another composite function that's composed by an exponential and a rational in its exponent. Well, while the domain of the exponential function by itself, it's all real numbers, let's have a look at the expression in the exponent. And then we have a rational expression for which there's a variable in the denominator. So the numerator y can be anything, but the denominator x cannot be equal to 0. So continuous for all x, y in R2 except where x, or as long as x is not equal to 0. All right, so that is our only condition, that x is not equal to 0. All right, so, and again, if you want to use the other notation, so that is x, y, x cannot be 0 and y can be anything, right? Can be any real number. All right. A very classical problem when it comes to discuss the continuity is at the typical piecewise defined function. So like this one, f of x, y equals to this rational, and then we're going to have a condition for all x, y not equal to 0. Because, well, check the denominator. You notice how both of them can be 0 at the same time. Otherwise, the function is undefined. However, they're giving us a function value in the middle of nowhere. You know, like those functions. So just so you can see what this represents in a way, that's when you had something like a diagonal function, a diagonal function continuous, but then you have a function value that is defined somewhere else. All right? Yes, I mean the function is not continuous. The limit at x equals, let's say, 3. All right, for instance, the limit of the function at x equals to 3 is actually exists because we're approaching the same y value. However, the function value, it's not defined where the hole is, but it's actually defined at a point somewhere else, right? So the function is defined, limit exists, but it's not continuous because of the way the function is defined. So we may have a situation like this for functions of the variables, like this one. So number one, we need to check the 3 conditions that we stated over here, but now I'm going to give you the 2 variable notation for it. So that's number 1. Condition number 1 is the function value. So what is f of 0, 0? Well, so from the piecewise function, I cannot substitute 0, 0 in the first part of the piecewise function because actually, look at this condition. It's forbidden. You know, it cannot be 0, 0. So that's why I need to go through the second part of the piecewise function. So they're telling us here that for x, y equals 0, 0, the function value equals to 1. So that's the first condition, right? Condition number 2. Limit as x approaches 0, y approaches 0, for x to the fourth minus y to the fourth over 2 x squared plus y squared, and that equals, okay, so if we try direct substitution, so notice in this case we can try direct substitution because we are not evaluating the function. We are finding the limit. So that's going to give us for sure, okay, 4 times 0 to the fourth minus 0 to the fourth over 2 times 0 to the second plus 0 to the second. That's for sure 0 over 0, which is good. All right? This is good because that means we can potentially do some algebra or L'Hopital, not L'Hopital's rule in this case, because we don't have a repeating pattern like those limits from yesterday. Well, so it looks like we can do some factoring to clear the 0 over 0 factor. So that is. In the numerator, notice how we have this difference of squares. So that is limit x approaches 0, y approaches 0. What quantity squared for x to the fourth? That means 2x squared minus y squared and 2x squared plus y squared. All right, everything divided by 2x squared plus y squared. Now, see how we may divide out these two factors. Those are actually the factors that are causing the 0 over 0, which is giving us the indeterminate form. So that's going to leave us with the following. That is limit 2x squared minus y squared, x approaches 0 and y approaches 0, and that is, what's that? We may go ahead and try direct substitution again, and that's going to give us a 0. All right? Okay, so while this is the value of the function, this is the value of the limit. All right? Now we need to check the third condition. Number 3 is f of 0, 0 equal to the limit of the function f of x, y. As x approaches 0, y approaches 0. Is this statement true for this case? No. No. Therefore, f of x, y is not continuous at point 0, 0. All right? So it's not continuous at the origin. And again, the picture here is like the one I drew a little bit at the top, where we have the point somewhere in the middle of nowhere, when not on, it's a point not on the surface. So in this case, like in the previous case, well, that's a point not on the line. In space for this function, that'll be a point not on the surface. All right. Okay. So, okay, is that it? Yeah, because the other limits we already finished. Okay.